we've been talking about the laboratory measurement method in chapter 9. I think we can finish it today. Okay. So we've seen the different excitation mode, right? Using impulse and random noise and the wavelet and the sinusoidal signal. And if you apply the impulse, the frequency content in the impulse has wide range of frequency band. Right? And the random noise also has the broadband spectrum of the frequency. And wavelet will have a certain band, and sinusoidal excitation will have only single frequency. So when you do the resonance testing, you apply the sinusoidal signal as you sweeping the frequency. And from the amplitude of the acceleration, you can get the frequency response like this. And the resonant frequency will give you the velocity. And from the half power bandwidth or the single degree of freedom system curve fitting will give you the damping of that. And I think we've done that. And we've seen the different damping estimation method. And so the 2-point estimation is the same with the half power bandwidth method. And this will give you, from our experience, it gives you the highest damping ratio among the other method. And the logarithmic free vibration decay also can estimate this delta and also alpha and the damping. Also curve fitting too. So, and when you estimate the strain, for example, in the resonance testing, I don't have it here. So you draw the G, the shear strain versus shear strain curve, right? Let's say that if I can use this one. Okay. So gamma versus G, right? And you have to estimate the shear strain to draw the curve. So curve normally looks like this, right? And as we talked before, when you have a cylindrical specimen, the shear strain is different from as you go away from the center of the specimen, right? So at here, you don't have the shear strain will be 0. At the edge of the specimen, you have the shear strain at maximum, right? So the representative shear strain, gamma, is the maximum that occurs at the 0.8, so 80% radius. So here, 0.8 R. At this point, you can get the representative shear strain. And this is an average strain for the volume of a specimen. And maximum stress displacement can be obtained from the maximum acceleration time divided by the frequency, resonant frequency square. So this is because the acceleration is second order of derivative of the displacement, right, with respect to the time. And hyperbolic relation, using the hyperbolic relation, we can get the shear modulus versus the shear strain curve. Okay, so small strain measurement have a least error in the estimation of the shear stiffness and the shear strain, so that this curve can be, the stiffness, small strain stiffness can be accurately performed on the solid rod specimen subjected to torsional excitation. So that this measurement can be justified by this all the evidences. And there are several comments or the discussion that we can think about the resonance testing. And measurement at different frequency is not easy to obtain the frequency dependent wave velocity and attenuation. And in the high frequency, mode coupling and noise, because of the coupling mode and the noise is difficult to get. And at lower frequency, you have a mass, so that adds the adding complexity. So for example, when we get the velocity, we estimate the velocity at this frequency, right? For example, this will be like 102 kilohertz, right? Or 3 kilohertz. So when you determine the velocity from the resonant testing, you can only obtain the velocity at that frequency. You don't get the velocity at the higher frequency or the lower frequency. It's going to be very difficult, right? It's difficult to control the frequency. So that's what it means. And testing effect, specimen aging due to repeated excitation. It's in particular when you apply the high strain. So it's like a strain hardening behavior. So as you excite more, this soil gets more compacted. So soil, if you start from the loose state, in the end, after the experiment, it's gonna be changed. The density will be changed. Density will become higher because it gets more compacted. So it's like you are applying some vibration to compact the soil. When you do the torsional shear testing, sometimes you go above the elastic threshold shear strain. So in that case, the specimen can be strain hardened. So for example, when you get the G curve over shear strain, if you do the testing, the shear strain larger than the threshold shear strain, then you may cause the strain hardening. So, and this will result the density increase. And in the resonant testing, since you have a cylindrical specimen at the fixed condition and the free condition at the top, and you have a mass with the wing, right? And this rotates, right? And if you don't have the flat surface at the top, this will give you some flexural mode and different modes. So it's gonna have some like vibration in different mode, and that affects the result. So you don't want to have that. You have to have a perfectly horizontal surface. So here must be perpendicular to the pedestal, and the top platen must be perfectly horizontal, and deviation can take place, and the transverse motion can develop in this. And counter EMF effect, the coil and magnet system, the vibration of the magnet relative to the coil produces a counter electromotive force that affects the attenuation, and that's because of the inductive characteristic of the coil. And fixed end, so we assume that we have a boundary condition of the free and fixed, right? In the fixed condition, at the bottom you have the soil, and this is the bottom platen. And sometimes you can have the slippage between the soil and the steel plate. So in this case, your governing equation doesn't model your results properly. So you need to have a fixed end condition, and because of that, some people use their gypsum to glue the lower part of the soil specimen, right? So that they can move together. Right? And the stiffness of the fixed end, so at the bottom, should be at least 10 times the stiffness of the specimen. So this should be a steel plate with a high stiffness. And coupling effect is the one that I just told you. Right? source transducer coupling in the resonant column is the interface between top platen and the soil. And free vibration decay, I think we've done that. So in the first mode, free vibration decay testing, a quasi-static rotation or displacement is imposed on the specimen. Then the specimen is released. The amplitude of the oscillation is measured with time. So one example is that maybe you can have a rock specimen like this, the one you did for the resonant frequency test, and you can have the wing at the top, and maybe you can apply the impact there, then this will give you the free vibration decay. Right? So from that, you can estimate the damping. Transient pulse. So here you can read this through. Self-healing is, so this is one technique to measure the velocity and the damping. Here you have a long soil column, and you can apply the impulse at the top, and the wave will transmit through the soil specimen, and then if you have the high impedance base, like a steel base, then this will be reflected, and you get the inverted signal, and then you have another signal coming, reflective one, and then again it's inverted so that you have the positive signal, and then negative, positive again. So the bottom figure is the response of that. Here you have firstly reflected signal, and then this is secondary reflected signal, right? Thirdly reflected signal here. Yes. So then, if you just pick up this one and this one, and then you can ignore all the peripheral frequency response. So self-healing means that you can cancel out all the peripheral electronic device effect here using the multiple reflection. If the X is input, H1 is the source and soil coupling, and H2 is the receiver and the soil coupling, then signal that enters the specimen is X times H1 by the convolution, and the first reflection X times H1 times H soil, and this is the response of the soil, impulse response of the soil. The one that we want to measure. So the received signal at the bottom will be Y1, and that's X times H1 times H soil times H2. So H2 is the coupling between the receiver and the soil. And from the second reflection, because the wave will go back and forth by 2L, so you can multiply the L square, the H soil square, and for the third reflection, again you can multiply the another H soil square. So then if you just divide the third reflection and the second reflection, then you don't have to worry about the source and the coupling between the source and this one, H2, coupling between the receiver. Right? So you have only the H soil left in the formulation. So then you can isolate the impulse response of the soil. This is a kind of a self-healing system. Another example for the attenuation measurement is the spectral ratio method. And amplitude of the particle motion can be expressed with this equation, A2 omega times C2, and C1, C2 are the frequency dependent coupling coefficient. And here A1, so you have the source around here, and wave goes and transfer through the point A and point A2. So then if you have the response from here and here, from that you can express the oscillation with this term here. This is the amplitude at the A1, and this is the geometric spreading, right? The distance R1 over R2, and this is material intrinsic property, and T is what? Transmittance coefficient, so that's for the scattering, and we are interested in this minus alpha, or the alpha that indicates material damping. So if you divide A1 over A2 in the logarithmic scale, here you have this equation. And if you plot this spectral ratio, this is called the spectral ratio, over the frequency, then this is just the y-intercept. Right? This is the y-intercept, and this is the linear curve. So from the slope, you can estimate the damping, but you need to know the velocity, right? And the distance. So this is called the spectral ratio method. So that means that you have one source, and if you have two accelerometer, or the sensors at different location, from the amplitude of detected by each sensor, you can calculate the material damping. Other method. This is just a simple principle. When you have a first mode resonance, this is the standard for the quasi-static testing or the dynamic testing. So when you apply the frequency lower than the first mode resonant frequency, FR, then we call it quasi-static testing. And when we do that, we look at the resonance of the soil. And here, if you apply the wave with the frequency larger than the resonant frequency, we look at the wave propagation. So this, you have a whole specimen oscillating up and down, so that compress and extend, compress, extend. And in this case, you have a specimen, one point, here is the source, wave propagate to the receiver. You can think about the picture. You can picture this with the frequency dependent behavior. At the high frequency, it's a wave propagation behavior, and low frequency is a quasi-static stress strain concept. So from this, you can calculate the damping, and from the slope, you can get the stiffness, right? Stress strain curve. Huh? Okay. In 5 minutes, let me show you some example of using the ultrasonic transducer. ultrasonic transducer 지금 우리 있니? 가자. Inside you have a piezo material. Piezo material, what's the piezo material? It converts the mechanical energy to electrical energy, and if you apply the electrical energy, it deforms, so it translates to the mechanical energy, right? So you apply the high voltage to the electrical energy, this piezoelectric material, then they're gonna deform. They will deform, and then it generates the wave, right? So excitation. So depending on the, and inside you have a two wire. That's for the, maybe one side is positive and the other side is the negative part. So you need to have a coaxial cable, right? And have a casing, and backside you have a backing material. And this backing material decides the attenuation of this transducer. So if you have a stiff backing material, you have very high reflective wave. So then that's going to be this kind of a signal. And if you have very soft backing material that has a high damping, then the output signal will look like this. Right? So the damping dependent, the ultrasonic transducer is because of the damping. So people design this backing material very carefully. And matching layer, insulator, so thing. So this is a coaxial cable, and this is a ultrasonic transducer. So inside it has the piezo material, and you can see that outside is the shielding, so it's a negative. Yeah, that's outside the shield, and the inside you have the core line that applies the voltage. Let's see and circulate it. So one example of the use of the ultrasonic transducer is this. You have a soil chamber. How big is it? 10 centimeter, 1 centimeter, 1.3 centimeter, 5 centimeter. It's a 3 centimeter, so I think it's about 20 centimeter, right? And you have a silica floor layer. So it's a silt layer, and so you have the sand and another sand at the top, and it's fully submerged in water. And what they do is that they scan it first, and then they apply the impact at the bottom, and they disturb the soil, and then they scan it again. So here, this is the before liquefaction. So before they impact it, so you can see that here is a strong reflection at the water and soil boundary because of the impedance difference. After that, you have another interface between sand and silt, right? So there's another reflection, and another reflection is from what? The silt and sand interface, and at the bottom is the aqueo, I think the base and the sand. It's quite flat, right? So they acquire the signal as they move their one transducers. Then they just plot it in the x-axis. And after they are liquefied, after impact, they have the hump in the soil, and that hump was detected by this ultrasonic transducer. So here, water, right, again, and the surface of the soil, surface of the sand has settled down a little bit, right? And also the middle layer is got settled down. So using that, so in the bathymetry exploration, so in the earth science, with the ship, they have a very big sonar, and they just scanned all the surface of the sea bottom, and they can get the morphology and the altitude inside the sea. Okay? And the near far field. So because this is not the point source, it has a certain diameter. So transducer is not the point side, and if we assume that the transducer, the piezo material deforms flatly, then you have several points of the excitation, and this wave will overlap each other, so that's why that you have some near field effect. Okay? At some point, at some region, you have the wave that's not P or that's not S or any body wave. But after certain wavelength, then it becomes the P wave or it becomes the S wave. Right? So it needs to have some distance to be able to form as a body wave. And that range is called the near field. And near field, it can be calculated using this equation. So in far field, in solid, here, in near field, the strong coupling between the P and S. In far field, now it becomes separated into P and the S wave components. So in the near field can be calculated using this equation, right? I square over lambda, and the far field you have some side lobe, so it's kind of spread a little bit, but you have a separation between the P and S wave. So if you calculate the near field region using this equation, how much would it be? For example, this one is the diameter is 0.5 inch. So in centimeter, how much is it? 25.4 millimeter over 2. That's 127 millimeter. So R is around 6.35, right? Millimeter. So if you calculate the NFL, R square over R square times F over V, 6.35 times 10 to the negative 3 square times 100,000 over 2,000. How much is it? You can cancel 1,000 and 1,000 and 550. Then 6 square times 10 to the negative 6, 50. Approximately 36. That's around 1.8 millimeter. Right? So I think it's going to be around 2 millimeter. Is it? So the near field of that ultrasonic transducer is around 2 millimeters. So you have to have a distance above that. A distance longer than the near field distance. So here, intensity. The near field of a pair of identical transducers is studied by aligning the submerged source and receiver transducer and gradually changing the distance between them. And here the diameter was 3/4 and 400 kilohertz. In the case, how much would that be? 500 kilohertz. So F 5 times, that should be 2 times 5, so 10 millimeter. And the R is 3 times larger, is it? Yep, 1.25. So here is a diameter is 0.5. The diameter is a 0.75. So if you calculate that, theoretically, the near field region is around 3 centimeters, 30 millimeter. And when you get the intensity, you can see that that's decreasing as you go further away, and this is the experimentally determined near field. So it's pretty similar to each other. That's around 30, 40, 50. And the directivity is after the near field, when you are a far field, it starts to spread. The energy will spread. So actually, it's not like laser. If you have a laser, then it doesn't spread. Right? You have a very good directivity. So divergence angle will be very small. But in the case of ultrasonic transducer, the sine phi, the divergence angle is about 1.2 times lambda over d. Then you get this kind of amplitude response. Here, you fix the source at here, and you're moving the receiver from the center to outside. Then you collect the amplitude, and you can see that this is the amplitude detectable by the receiver. So around 2 centimeter, plus or minus 2 centimeter. And here, yes. And also the directivity can be measured. So you have a receiver and source, you're rotating it, right? And so I think the 80 degree, 180 degree. Then at the side, if you're at here, that's around 0 degree, right? If this is 90 degree, this is 0 degree, and at the 0 degree you don't get any signal, and you start to get a little bit of signal, and you have the maximum signal when you align perfectly, and also it starts to decrease.